Morning, everyone. I hope there is a higher probability of you enjoying what we are about to discuss right now. So, as we move further from Chapter 5, we will be discussing Lesson 5.2, which is the laws of probability. Is it perhaps familiar? You may have already encountered it during our high school years. But right now, allow me to share my knowledge about it to you.
Before proceeding to the real deal, let's start first with the question. What exactly is probability? Probability, by definition, is simply how likely something is to happen. Whenever we're unsure about the outcome of an event, we can talk about the probabilities of certain outcomes, how likely they are. The analysis of events governed by probability is called statistics. So to put it simply, probability is your chances. For example, in a lottery, the chances you have of winning is a probability. Similarly, Pag-asa, for instance, said that there is 60% chance of raining tomorrow. The 60% that was given is a probability, which means there is a higher chance of raining tomorrow because it's greater than 50%. Types of events. I've included this here as we will be encountering it or use these terms a lot in our discussion. So we have here mutually exclusive events. Mutually exclusive events are things that can't happen at the same time. For example, you can't run backwards and forwards at the same time. The events running forward and running backwards are mutually exclusive. Tossing a coin can also give you this type of event. You can toss a coin and get both heads and tails. So tossing a heads and tossing a tails are mutually exclusive. Yes, as it says, these are events that can't happen at the same time. From the word exclusive, which means unshared, individual, private, we already have the grasp of it. The simplest example of it is inhaling and exhaling. Did you ever met a person who's inhaling on the right hole of the nose while exhaling on the left? See? It's definitely mutually exclusive then. Next is non-mutually exclusive. Non-mutually exclusive events are events that can happen at the same time. Examples include driving and listening to the radio, even numbers and prime numbers on a die, losing a game and scoring, or running and sweating. Basically, it's just the opposite of mutually exclusive. This means that the events given could happen simultaneously. More examples are sleeping and snoring, smiling and taking a picture, writing and listening, and many more. Third type is dependent events. So how do we know that events are dependent? Here it says that two events are dependent when the occurrence of one event influences the probability of another event. Simple examples of dependent events: not paying your power bill on time and having your power cut off, being the first person to enter a movie theater and finding a good seat. For me, it's like cause and effect, where the first event affects or can change the course of the second event, and vice versa. For example, listening and understanding what has been said. Obviously, the more you listen, the more you will understand. Listening affects how well you understand what has been said. That's why it's dependent event. Another one is practicing and performance ratings. How about independent events? Independent events are just the opposite of dependent events. In probability, we say two events are independent if knowing one event occurred doesn't change the probability of the other event. For example, the probability that a fair coin shows heads after being flipped is still 1/2, no matter how many times you repeat it. The color of your shirt and the weather today. Are those two events related? Does the color of your shirt changes or affects the weather? No, right? That's exactly what independent events are. Events that are completely unrelated to one another. How to read certain symbols. So it's important to know these symbols because we'll be using it in our discussion and computation. So the first symbol is read as the probability of A, where A is an event we are interested in. Second is read as the probability of A given B occurs. And third is read as the probability of not A, or the probability that A does not occur. Now we can finally move to the basic laws of probability. There are 6 rules that I've included here, but this is not all of it. There may be some that I missed, but these here are the basics. Let's discuss first rule number 1. Rule number 1 states that the probability of an impossible event is 0. The probability of a certain event is 1. Therefore, for any event A, the range of possible probabilities is probability of A is greater than or equal to 0, but lesser than or equal to 1. Remember that there is never a negative probability, nor more than one. If the event will never or impossible to happen, then the probability of it happening is 0 or closer to 0. But if you are sure that it will happen, then it is 1 or closer to 1. Anything within this range will tell you how likely the event will happen. Higher probability means higher chances. To further understand it, we must proceed to the sample problems. 1. A flower shop only has 68 flowers left before it closes. 12 roses, 10 sunflowers, 25 tulips, 7 carnations, and 14 daisies. If the owner decided to give you 1 flower for free, what are your chances of getting A. A hyacinth, B. Any of it, C. A tulip? Let's solve it together. So we must always remember that the probability of an event is expressed as probability of an event equals a number of favorable outcomes divided by sample space. For letter A, we take number of hyacinths as favorable outcomes and total flowers left for the sample space. 0 because there are no hyacinths, divided by 68, that's why it's 0. Letter B is just the same as letter A. Since it says any of it, so our favorable outcomes is just the number of flowers left divided by total flowers left. So 68, number of flowers left, divided by total flowers left, which is also 68, equals 1. It's actually 1. So therefore, the probability of getting 1 flower of any kind is 1 or 100%. Now, solving for C is just a piece of cake. Next is rule number 2. The second rule states that for S, the sample space of all possibilities, probability of S is equal to 1. That is, the sum of all probabilities for all possible events is equal to 1. Recall the party affiliation above. If you have to belong to one of the 3 designated political parties, then the sum of probability of R, probability of D, and probability of I is equal to 1. Means that all the probabilities of one event will always equate to 1. Even if there are countless of possible outcomes, it will always sum up to 1. In tossing a coin where there are only 2 possible outcomes, the probability of getting a tail is 0.5, and the probability of getting a head is also 0.5. When we add the 2 of it, it will sum up to 1. This proves rule number 2. Let's take a look at the sample problems to further prove this rule. A university has 83% probability of passing board exams. 11% probability of failing, and 6% of not taking board exam. What is the sum of all its probabilities? Number 2. John decided to pick the subject for his case study in BS Statistics 1A class, where his probability of choosing a female is 17 over 23 and 6 over 23 for a male. What is the sum of all the probabilities in this event? For number 1, we just have to add the probability of passing, failing, and not taking to prove that it will really equate to 1 or 100%. We should always remember that the probability of 1 is just the same as 100%. If you wish to convert a probability which is in percentage form to decimal form, you just have to divide it by 100. That's how I got this 0.83. 83% divided by 100 equals 0.83. Just have to do the same thing for 11% and 6%. Going back, we just have to add all the values which results to 1. It never go lower or higher than 1, which proves rule number 2. For number 2, we just have to prove that the probability of picking female and picking male will equate to 1. Since it's in fraction form with similar denominator, we just have to add the numerator and copy the denominator. There are 17 females, so 17 plus there are 6 males, so 17 plus 6 over 23 equals 23 divided by 23, which is equal to 1. We proved that the sum of all probabilities of this event is really equal to 1. Then we have here the third rule, which is the complement rule. Probability of not A is equal to 1 minus probability of A. This rule builds upon the mutually exclusive nature of probability of A and probability of not A. These two events can never occur together, but one of them always has to occur. Therefore, probability of A and probability of not A when added is equal to 1. For example, if the weatherman says there is a 0.3 chance of rain tomorrow, what are the chances of no rain? So let's do the math. Probability of no rain or not raining is equal to 1 minus probability of raining equals 1 minus 0.3 equals 0.7. So the probability of not raining tomorrow is 0.7. Complement rule simply means the probability of not getting the given event. It has mentioned here that two events have to be mutually exclusive. That means that there should be no intersection of the two events, like the example rain and no rain. Getting the probability of not raining using the probability of raining is only possible because when it's raining, it can't really not rain. We can't have the two events at the same time. I have prepared sample problems here to visualize it better. Number 1. What are your chances of failing the midterm exam if your passing rate is 84%? Number 2. What are the chances of not getting a spade in a standard deck of cards? In number 1, using the complement rule, we subtract 0.84, the probability of passing, from 1 to get the probability of not passing. 1 minus 0.84 is equal to 0.16. Therefore, probability of not passing is 0.16 or 16%. Number 2 is just the same. First step is to get the probability of getting a spade. There are 13 spades in a standard deck of cards which has 52 cards in total. That means the probability of getting a spade is 13 over 52.
So probability of not getting a spade is 1 minus probability of getting a spade. To make it easier to compute, I converted 1 to fraction form and then subtract it by 13 over 52, which is equal to 39 over 52. Then simplify by dividing both numerator and denominator by 13. Therefore, the probability of not getting a spade is 0.75 or 75%. Fourth rule is also called the addition rule, which states that the probability of A or B is equal to probability of A plus probability of B minus probability of A and B. If A and B are mutually exclusive events, or those that cannot occur together, then the third term is 0, and the rule reduces to probability of A or B is equal to probability of A plus probability of B. For example, you can flip a coin and have it come up both heads and tails on one toss. For the addition rule, formula for exclusive and non-exclusive events aren't really different. It's just that the formula for the mutually exclusive events is modified or simplified because we already know that in mutually exclusive events, there will never be an intersection of the two events. That's why its formula becomes probability of A or B is equal to probability of A plus probability of B, leaving out probability of A and B. So let's move to the sample problems. Number 1. If a die is rolled, what is the probability of getting A? A 3 or a 7? B. A 1 or a 5? Number 2. In a deck of cards, suppose you have to choose one. What is your probability of getting? A 4 or a spade? In rule number 4, it is important to identify first what type of event we are dealing with to have the accurate formula to use. As what you can see in a die, there are only 6 dimensions, which means that the number of dots are only from 1 up to 6 every dimension. Number 1 is clearly mutually exclusive, that's why the formula I used is this. Probability of a 3 is 1 over 6 plus probability of a 7 is 0, which is because there are absolutely no 7 in a die. Add up the two values together, therefore the probability of getting a 3 or a 7 is 0.1667 or 16.67%. You just have to do the same thing in solving for letter B. I'm sure it's easy for you now. So we get 1 over 3 after we simplified it. So the answer is 0.33 or 33.33%. Number 2 is non-mutually exclusive events because it could happen at the same time. That's why we are using this formula. Probability of getting a 4 is 4 over 52 because there are 4 fours in a deck of cards. 13 over 52 probability of getting a spade, and getting a 4 and a spade is 1 over 52 because there is only 1/4 of spades in standard deck of cards. So using addition rule, we get this result. The fifth law of probability is the multiplication rule, which states that probability of A and B is equal to probability of A times probability of B given A, or probability of B times probability of A given B. If A and B are independent events, we can reduce the formula to probability of A and B is equal to probability of A times probability of B. The term independent refers to any event whose outcome is not affected by the outcome of another event. For instance, consider the second of 2 coin flips, which still has 0.5 or 50% probability of landing heads regardless of what came up on the first flip.
Take note that in multiplication rule, there are different formula for independent and dependent events. Independent events simply multiply the probability of A and the probability of B, unlike dependent events in which we have to consider event A. Why? Because in independent events, the first and second event are completely unrelated. They cannot affect one another. I have prepared sample problems here for us to have a better understanding of multiplication rule. So number 1, Anna wants to buy a new phone with a case. The store offers iPhone, Samsung, and Oppo. For the case, there are 5 available colors: pink, yellow, green, violet, and blue. What are the chances that she will choose Samsung with pink case? Number 2, if you have to pick 2 cards from a standard pack of cards, one after another, without replacing the first card, what is the probability that the first card is the ace of clove and the second card is a diamond? First, we need to identify the type of event in the problem. For number 1, it's independent, so we'll use this formula. Simply multiply the probability of choosing a Samsung, which is 1/3, and probability of choosing a pink case, which is 1/5, to get this result. In number 2, the events are dependent. So the formula we should use is this. Probability of picking ace of clove, which is 1/52, times the probability of picking a diamond given ace of clove, which is 13/51. The numerator remains the same because picking an ace of clove on first draw will not affect the probability of picking a diamond on the second, while the denominator becomes 51 because the first card wasn't replaced, so the sample space becomes smaller. After that, we just simplify it to get this result. Lastly, conditional probability. Conditional probability states that probability of A given B is equal to probability of A and B divided by probability of B, or probability of B given A is equal to probability of B and A divided by probability of A. The conditional probability of an event B is the probability that the event will occur given the knowledge that an event A has already occurred. This probability is written probability of B given A. Notation for the probability of B given A. In the case where events A and B are independent, where event A has no effect on the probability of event B, the conditional probability of event B given event A is simply the probability of event B, that is, probability of B. In conditional probability, we consider the previous event to come up with the probability. This is usually used in dependent events. From the root word condition, this obviously implies that the occurrence of the first event would affect the probability of occurring of the second event. We have sample problems here to further discuss conditional probability. Number 1. Suppose you have 27 shirts, 3 of which are green, 7 are white, 5 are blue, 2 are pink, and 10 are black. What are your chances of drawing? A. A black shirt if 2 of it are still in the laundry. B. A pink shirt if you lost 1 of it. For number 1, since we initially have 10 black shirts, so our favorable outcome is 10 over the total shirts we have, which is 27. But then it was stated there that 2 of the black shirts are still in the laundry. So we have to subtract these 2 shirts from both numerator and denominator. Therefore, the probability of drawing black shirt, given that 2 of it are still in the laundry, is 0.32 or 32%. The process of getting the answer for question 2 is just the same, so it's easier for you to solve it. conclude our lesson for today, may I ask you a question? Have you ever hoped for something to happen? Well, I really think that we keep hoping for it to happen even though it seems too far-fetched, because we think, or probably we know, that even in just a little probability, it will happen. Probability in life isn't just always about numbers we visibly count, compute, or solve. Sometimes it's just doubt, hope, regrets, decisions, and crossroads. Probability is sometimes dressed as a question, what if? But probability makes us ready. If we know how to weigh it and use the advantage of solving for probabilities, even though we don't know what the future brings, we will know what step is the best for us. Probability makes us confident and flexible. From this lesson, we learned different laws of probability. And I hope as you listened, probably not, you've improved something in you, especially your decision making. With probability, we can expect for things that are more likely to happen. And with that, we can monitor our expectations for lesser disappointment.